I think you can use this one later on here, but it's only for a room. I think if you feel that is enough, we don't have a lot of people here.
Yeah, they just hear me then. Yeah.
So this event is also a hybrid one. So what we are doing here, people on the internet can see each other. Okay, so good afternoon, everyone. Thank you for joining us today. Everyone in person and also everyone online as well. So this and joining this very exciting event. So this event is sponsored by Crane. As you can see there. So Crane is an EPSRC network that is dedicated to strengthening, the UK cybersecurity research community. And over the next 2 years, Crane would support a series of seminars across different regions in the UK. So in Wales, then this initiative would be coordinated by Yang Liu, yes, by Mukesh and myself. So we are from the Science Security Group from Swansea University, but also together with Professor Omar Rana from Cardiff and George from Cardiff as well, yes. George Cardiff and other colleagues, and also with the support from obviously from Marcus, the co-lead of the security groups. We also have Mabruka. I don't see Mabruka yet today, but Mabruka is the cybersecurity research lead from University of South Wales, and also I think John is been coming here. John is the director of Cyber Wales. Together we aim to bring a vibrant seminar series that foster collaboration and also innovations to cyber security research in UK, in Wales, and in UK. Today marks the first seminars of the series in Wales, and we are very delighted to have Dr. Berry Schoenmakers. Hope I say your name right. Yeah. So Berry is a globally recognized expert in cryptography and especially in secure multiparty computation. So his research provide a bridge between theoretical foundations and also practical applications that enable the privacy-preserving computation, which is a very crucial area for the future of secure systems. If you are interested in if you are interested in programming, interested in security, cryptography, I would say again multi-party computations and privacies, and this seminar would promise to be one of the ones that would be insightful and also inspiring. I would hope that would open doors for new research in cybersecurity. So after the presentation and the question and answer today, we will have about 5-minute break for tea, coffee, anything for the cake as well. And then we would have a panel discussion about different aspects of secure multi-party computation. So I would think about like the theories like implementation, like applications, and also future direction as well. But with no further ado, then please join me to give a warm welcome to Dr. Berry Schoenmakers. Thank you. Maybe I need to ask Roberto, can you stop my sharing so that
I'm sharing.
You are sharing.
Yeah.
Okay, thank you.
Then I.
So just to confirm, so Roberto, can you see Barry's screen?
Yes, I can see. I think it's the present part I can see.
Oh yeah, wait, so that's wait.
So you are sharing the whole screen, right?
Yeah, because it's a duplicate on that one that I have to stop that one. And then picks up this, but I think that this might be okay for the.
I still can see the present
So there is a switch here somewhere.
Yeah.
part.
Click OK here.
Oh, swap, yeah. I don't know.
Now it's perfect. Thank you.
People here would be, let me try.
Yeah, and it should stop the presenting mode of it. Is that possible? Yeah. I don't know how to stop this.
So this one to stop.
No. To stop the split screen that it does the presenter mode. And let's see.
So now they see that okay. So let me try one more time.
But I think this is good enough for the online.
Duplicates, nice now. So this one. Right?
Oh,
Yes.
yeah.
Okay, thank you.
Genius.
Cool, perfect.
Yes, yeah. So thank you now for the nice introduction, and thank you to Crane and to Mukesh for arranging this visit, so that I can give, as I understand, the first talk in this seminar series of your Crane enterprise. Wait, but this.
You could hide it. To click on more. Oh yeah, just the one screen.
One more.
This one.
Yeah,
Okay.
it's fine. That's
Yeah. And this, okay.
Oh.
No.
Probably go more. Yeah, hide floating meeting. No.
Oh, that's one, and then
Floating.
Floating.
Go down. Yeah. Oh.
yes. So I think you're well on time. No sense of time. So okay, yeah. So so my name is Berry Schoenmakers. I'm from the Netherlands, where I'm with the Department of Mathematics and Computer Science in Eindhoven. And there I'm in the crypto group. So crypto is my background, as now already mentioned. And within crypto, multi-party computation is one of the main topics that I work on already for many years, and I still like to work on it for many years to come, I hope. And it's a pleasure for me to share some ideas with you about this topic this afternoon. So I've divided the talk for today into these three parts. First, some general background and some motivation, also in terms of use cases. Then some more technical protocol ideas at a high level, that's tell you a little bit how MPC can be accomplished. And then we turn to this practical form of MPC in terms of this Python package that you can download, that you can use to run these MPC protocols for yourself. Well, for yourself is maybe not so interesting. You need some other parties as well to connect with so that you can do something interesting. But actually, if you test the programs that you write, you run it for yourself and then try it with others. Okay, so MPC is one of the several techniques that we have to enhance the privacy in situations and lots of applications. So there's a lot of demand for that privacy of data that belongs to individuals, but also, for instance, hiding your identity when you interact online. That's another type of privacy. So here's an overview, and I picked this up. It's somewhat arbitrary, where things are organized in this way. Here's another one. The usual suspects, they show up again: private information retrieval, zero knowledge proofs, homomorphic encryption. So this is in a different mix-up, because in a way these things are not so easy to categorize. It's not that you do simply this or this. It's often a combination, and things are very much related. So private information retrieval can be seen as a special case of two-party computation, for instance. Homomorphic encryption is also used in secure multi-party computation. So it's not that these things are independent of each other. What I like to do is to take a more cryptographic point of view for these privacy-enhancing technologies. And I often like to contrast crypto 1.0, so to speak, with 2.0, where 1.0 is about classical crypto. So you want to send a secret message across the channel, and you don't want anyone to eavesdrop on that communication. That's the classical concern, and we use encryption to deal with that. Or you want to authenticate your message such that you can show that it comes from you and not someone else. You use signatures. So these are the traditional primitives that we know from crypto since the 70s or so. And they mainly protect against attacks from the outside. We send it to someone else, the other endpoint we trust, but we don't trust the outsiders. Now in crypto 2.0, that we have the situation that we don't even want to trust or cannot trust our protocol partners. So the parties that we communicate with or that we interact with are also not necessarily honest. So we want to protect against that kind of threats. And for that, we have a long list of primitives that has been evolved over time. So already at the early days, soon after RSA was invented and patented, even in 1977, 76. In 78, people already thought of the idea to do homomorphic encryption, encrypt with data while not seeing the data, keeping it in encrypted form. They could not realize this fully until the breakthrough established by Craig Gentry in his PhD thesis. Was a good thesis, but he was already like an older candidate. He was in his mid-30s when he finally did his thesis, so that's not really fair. But he did this breakthrough as his thesis to do any kind of computation on encrypted data. So this is one technique that's also in vogue these days, but it's basically less efficient than what we can do with MPC. because in multi-party computation, we allow for interaction between the parties. So we can interact and thereby obtain more efficient solutions. So, yeah. But so here's a long list, and we will see a few more of these things this afternoon. But I highlighted this one, of course, and this one is also very well known. Yeah, but if someone generates a zero knowledge proof to prove knowledge of some secret value, yeah, then we require that proof because we don't trust the prover to be honest. We need a proof to exclude that someone is misbehaving. And also the other way around, if you show a proof to a verifier and there's interactive verification, then we don't trust the verifier to issue random challenges. If the protocol prescribes that, the verifier might pick the challenges in an intricate way, maybe to gain an advantage and try to find some information about your secret. So that's the point, and that makes these primitives much harder to achieve, that we cannot trust the others. Yeah, so for doing this, yeah, in a way we came a long way, and we have this nice gadget that's an antique gadget. Well, I don't have it. I just found this picture on the internet, and we can contrast it with this nice thing invented by a colleague of mine from Eindhoven University, Tom Verhoef. I have it here, a 3D printed thing for later if you like. So this here is doing a special two-party protocol between Alice and Bob to do some matchmaking to see if they are interested in each other, if there's a match. But if there's no match, then for instance, if I'm Bob and I already I'm not interested in Alice, but I think, oh, maybe let's run the protocol, then I can find out if she was interested in me or not. But if I'm not interested to begin with, then by running the protocol, I should not learn whether she was interested or not, because we already know that the outcome will be no match. Then Alice's input doesn't matter, and therefore I should not be able to find out what her idea was. And now we have to see. We can do this, hopefully. We can show this. So I picked yes for Alice, no for Bob. And it's a bit slow. The idea is that we have these 5 pieces, one separated piece, and then 2 pieces provided by each side, by both sides. And then we close them, and then we spin the wheel. It's a bit slow, but it doesn't really show the spinning. And then we look for the result. That's the mismatch. That doesn't look very nice. But, well, let's be optimistic. Let's see what happens if we they both think, okay, this is a good idea. And the spinning is not so visible, but that looks much better. So this is what it shows when there's a match, and when there's a mismatch, whatever the mismatch is, no, 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 yes, no, all these ones, they are indistinguishable. You don't see any difference. And this is a key idea in cryptography, that things are indistinguishable there's no information about the no, yes, no, whatever combination, if there's a mismatch. So that's the idea. And actually, so TNO, some organization in the Netherlands, they also made a nice video for this, but they presented this as a second to see if they're interested in the second date, because imagine that you want to do this, but you do it to ask others for a first date, then already the reason because you're asking for this, it's already saying that you're kind of interested to engage with her. So that, but by doing this to find out if they are into a second date, they have these dating shows on TV, and then they have to decide, do we do a second date? Then this one would be a fitting solution. Yeah, so this is actually a very powerful device. And we will get back to this later. In the introduction, I now want to say a bit more about MPC. So the background, so this nice picture, what does it show? Maybe anyone knows it. This wild thing. This is like the Cambrian explosion, so it's really a long time ago that this picture was taken. But it's what happened in the evolution, and I draw the analogy with the evolution of these primitives, these MPC primitives, that started this time ago, but like in the 2010s, the last decade, that was also an explosion of MPC schemes and blockchain and all that kind of protocols were introduced. So what I mean, there's this kind of timeline, and we saw these primitives, encryption, secret sharing, oblivious transfer, and then multiparty computation was invented in the mid-80s. And then from then on, yeah, we started to develop somewhat simpler applications like voting. Auctions, they are already a bit more complicated. And then we had this explosion of frameworks and implementations in the last decade. But we are already in the 2020s, and that we could say, well, that's also about deployment, that there's now commercial enterprises, companies doing this stuff. And I'm very familiar with one such company, that because it's run by several of my former students and postdocs. They started this almost 6 years ago, and now they have 35 to 40 people, imagine, working on doing this MPC stuff in lots of projects, mostly within the Netherlands, tackling problems like elderly people taking the bus or not taking the bus to find out a connection between the usage of the public transport and say medical situations. And those kinds of data sets, they are not allowed to combine those things under GDPR and such things. And then by using MPC, they are allowed to combine those sets and draw conclusions. So there's typically these kinds of use cases, and I have a use case here, a nice one that they're also working on, and it's about vessels, boats, ships in the North Sea Channel, or North Sea. What's this? Let's go here. There it is. So imagine we have some information. Is this the zoomed in? Wait. But we have several data sources that have certain information. So this data source has some information about vessels. It shows like this. But that information is not enough to draw important conclusions. So we would like to combine it with further data sources. This one, it's in a different format, and combine all this and draw conclusions by performing a computation on this joint data set, but without revealing this data to anyone. So that's the so that can be data that's of very high value. So they want to do this extra effort to protect it. No, it's still that one. Not sure why. Okay, yeah. Now we have this. Yeah. Back here. So that's another example. Yeah, and a whole branch of use cases in a different direction is this goal of threshold cryptography. So as you may know, if in the context of blockchains, what people like to do often is to use a form of threshold signatures, where a transaction is only authorized if a majority of parties agrees to run the transaction. So they all issue a partial signature, and if there's sufficient many of those partial signatures, then they can create a threshold signature to okay the transaction. And that's often seen as a form of multi-party computation. And connected to this is distributed key generation, all these kinds of things is what people are doing, and there's really high stakes fire blocks. They are doing very important transactions with this, and they use this form of MPC, but mind you, they will use active security for this kind of protocols as opposed to passive security. Yes,
Barry, could you try to explain? So it appears that this not revealing of some kind of data is important. Can you explain where the non-revealing part would be sitting here in the threshold computation?
So that's a good question. So that's about the actual secret key. So the signature ultimately requires a secret key to issue the signature, to compute the signature. But that secret key doesn't exist in any single place. It only exists in terms of secret shares that are held by a number of parties. And the secret shares, those are the secrets. And to run the protocol, each party uses its own secret share to generate a part of the signature. And so there, the data is not meaningful. It's a key. It's a random sequence of bits. So there's nothing personal in there, but it's of value for the system. Yeah. Okay, so that's the first part. So now I want to show you some of these ideas that enable us to do this at all, well, very high level. So so I'm mentioning these parties, multiple parties, and they run a protocol together. And in doing so, they want to ensure that the results of the protocol are correct. that nobody can influence the results to their advantage. And the inputs that they use, and sometimes also the outputs, have to remain secret. That's a privacy concern. So and achieving these two together, it's like a conflicting requirement. It's easy to do one of the two, but to do it both, that's the challenge. And I've indicated here by and between to emphasize two different scenarios. If we do by multiple parties, it's sometimes called the outsourcing scenario. And that's typically what happens in voting or running an auction. So we might all be voting, and maybe all the people here on the campus, they might be taking part as voters. But for counting the votes, the so-called talliers, those are not all of us. Those are a designated small set of individuals or so that will actually do the tallying, the counting of the votes, and they run the MPC. But the voters are just providing input. That's typical of an outsourcing scenario. But you can also have that it's really between the parties. For instance, in a two-party case, the classical millionaires problem by Yao from the early 80s is to establish who is richer than the other one. That would be interesting. So to find out which of the two numbers is the largest one, but without revealing the actual value of those numbers, only the fact which one is the larger one. And nowadays, if you look into the literature, you will find lots of papers about private set intersection. So, for instance, an airline, there's going to be a flight from Cardiff to New York, and the US wants to check if there's any passenger that's suspicious or blacklisted. So then they compute the intersection between the list of passengers and the listed people, and if there's anyone in the intersection, then they do something. But that's a situation that arises in many places. Now, for this voting, as I said, so that's relatively easy, but although you can also have very complicated elections, but in a very simple election like a referendum where you have yes and no votes, it can be as simple as this. So we have 4 voters casting yes, no votes, and it adds up to 2. But if this is run by a single server, that single server will see all the individual votes, not just the total. So if we make a simple split into 2 servers, and we make sure that these 2 values add up to the desired vote, 0, 1, 0, 1, then these numbers by themselves are totally random. They have no information about the vote that's connected to it. And this tallier can make this total. The other tallier does also computes this total. And when we add this up, obviously, it still gives the final result. But in this process, neither of the talliers learned anything about the individual votes, and overall, we only got the total number of yes votes and nothing else.
So talliers don't collude with each other.
Yeah, that's the assumption. Yeah. Well, yeah. So, and if you don't trust it with 2 talliers, you can extend it to 5, and you can also do threshold versions. So that's the idea that you have to. But this is the simplest case that shows the effect. Now, about the secret sharing. So what we saw with these numbers, can be done in a mathematical way and with very with the highest form of security, namely information theoretically secure stuff. There's no information in either of the shares. So this is visual secret sharing. This is like a random what is it? Image of black and white pixels. And the other one is also random. So totally random, 50% black, white, no information in a single part. So even a quantum computer will be at loss or no chance. There's nothing to gain there. But then if we combine them, that's the genius of this scheme. We find a nice image. So this can be used. It was also proposed to be actually used for secret messaging in those old days when we still had the fax machine. So it's probably quite some of you will recall the fax machine. So the idea was that we would already send this ahead of time to the other side, so to keep this as a transparency, and then we would send a fax later that could still be updated to contain the message as desired, and then the receivers they would put it together and read the message. And it's a way to do cryptography without using a computer, really, without actual computation. And so some people at Philips did this actually. So here you lose contrast. And you see that white is not really white because we cannot cancel the black and white thing don't cancel. But people at Philips did it with polarized light, like the LCD screen has polarized light, and then you can cancel, and then you will regain contrast. Now, so that's one way to think of secret sharing, and we use it to do elections. The election relies on additions, and that's kind of easy. Mathematically, it's a linear operation, and the linear operations, like in many technical topics, are kind of easy. But the difficulty is with the nonlinear parts, multiplication of two numbers, say, or 2 bits even. Just multiplying 2 bits is already a very useful primitive. So let's see about that. Well, we already saw a solution, namely the thing that Alice and Bob did, the matchmaking, in a way, is this multiplication, if you think about it. So we have this table. If there's a match, yes, you can think of it as a 1. Less romantic, but simpler. And the other ones are zeros. It's like the AND gate. That's what the gadget does. So that's why it's a powerful gadget. And this is what we want to do. Also with bits and numbers. So this is the gadget again, but now we want to do it with bits and numbers, and then that's where modern cryptography comes into play. And I'm not going to show you these actual bits and numbers, but here's one well-known approach, well-known route. It's via the primitive known as oblivious transfer. So it's a strange primitive where we have 2 parties, one party on this side, and there's the other party, and they want to run this protocol where this side inputs 2 messages, M0 and M1. These can be just single bits. They can also be bit strings in general. The other side puts in a bit, a choice bit, and then that side gets the chosen message. That's the thing it gets, but about the other message, you don't get any information. So it's all or nothing. You get the one that you select, but the other one you don't see. So this is a primitive that you can build with public key kind of crypto. Think RSA, LGMO, that kind of stuff. You can build this primitive. So it's an expensive primitive. It's not just symmetric crypto. It's expensive in a way. And you can also do it in a post-quantum setting, post-quantum crypto. But once we have this primitive, we can do the AND protocol for two parties as follows. Look, we want to get the product x times y. And we will have x on this side and y on that side. But the x on this side is put in this place. And the 0 is put there. And the choice bit is y. And that exactly gives the result, because if y is 0, we select this one. So we get 0 as result. Yeah. 0 times anything is 0. So that's correct. And if y is equal to 1, we get this one. And that's x. So it still depends on x. But that's the correct value, because if y is 1, then x times y is just x. So that's already enough to show that with this primitive given, we can make the secure AND gate. And basically, this is what people do in MPC. Starting from this, you can build anything you want. Because you may know that the AND, or rather the NAND gate, the Sheffer stroke, is complete for computation. So once you have that one, you can do everything. And there's a famous paper by Joe Killian that shows that you can do general multi-party computation, even zero knowledge and all primitives, once you have OT. So it's so things are OT complete. OT is complete for lots of things. Now, but here I stress that this is expensive. It requires public key crypto. And that's because we do a two-party setting. And two-party setting is difficult because we don't have a so-called honest majority. Because we don't trust the other party. That's the whole point. So only one of them is trusted, but one is not majoring the other one. There's not more than one. So that's not enough. But with three parties, then two others are more than one. So with three parties, we can tolerate one cheating, one corrupt party. And we can do so in a very cheap way. So here is what we do. We still want to compute the AND, x times y. The output bit, it will be created in secret shares. They won't see x times y as a public output, but they will all obtain one share of the product. So here is what we do. This kind of helper party, Chuck, who doesn't have input of just there. Yeah, we are still safe. Yeah. So that party will just provide a random bit to Alice, but only to Alice, and another random bit to Bob. And they have the input bits x and y. So now they exchange these two bits. The x is masked by alpha, and this is XOR, modulo 2. And the y is masked by the beta. And with that, they they can all obtain their shares of the result. For Chuck, it's alpha times beta. For Alice, it's this. That's how we do it. Alpha times the value that it received. And for Bob, it's the value from Alice times y. And these together, we can verify, they add up to x times y, because we have the alpha times y, and alpha times y modulo 2 will cancel. And the alpha beta cancels. And what remains is this x times y over there. So this is a perfect solution. Also meaning it has perfect security in the cryptographic sense that it is information theoretic secure also against quantum computers. And it's very cheap. So these are just single bits. So you have to send these bits across. So maybe you need SSL or I don't know to protect those single bits. But otherwise, the computation is trivial. You can do it yourself if you like. While the OT stuff would require computers. That's public key with modulo huge primes and stuff. And this here, this direction is what we follow in MPC when we use honest majorities, like we do in MPyC. So this shows a essential barrier or step from two-party to three-party. So with two parties, we don't have a majority. We have to resort to expensive primitives, but with three parties, we can have perfect security in a simple way. And for M parties in general, if the number of corruption is less than half, that's an honest majority. We can also do it for multiple parties. Yeah, so that's, I think. Oh, I have this other slide inserted. So how is the time? Oh, kind of okay. Yeah. Yeah. So this is the last slide of the part 2 to introduce to you another technical idea that we often use in MPC is to use so-called random self-reusability. And I give 2 examples. One example is to take the multiplicative inverse of A, and we want to have 1 over A. And these brackets, they indicate secret share. These values are secret shared between the parties. We don't see them. So the input is secret shared and the output is secret shared. But we want to open something. This is in the clear. But what we open has been randomized perfectly by multiplying with some random R. And the random R was generated. That's a sub-protocol, but it's not too complicated, not too expensive. This is now a secure multiplication. We saw multiplication of bits, but we can extend this to, it's just a finite field. We do it modulo a big prime. Then we decrypt or open the product. We invert the product in the clear, so that's the nice thing. We need to invert something secret, but we do the inversion in the clear, so that's cheap. All the parties do it for themselves, and then we multiply this back again on this R, but then we say R cancels against this R, and 1 over A remains. Secret share. So that's a rather standard example. And here's another one that we developed a few years ago to do sine and cosine on secret shared values. So there's an angle modulo 2 pi given. We generate a random angle. But together with that random angle, we also generate already the solution for that angle. And that can be done efficiently because we have this under control. We know this angle. We make it piecewise. And then we also get this efficiently. And with that, we go like this. We open this value. And then we do this in the clear. We do a cosine and a sine in the clear. That doesn't cost any time. And we multiply them. This is like complex multiplication. And we get the result. So, and this is all implemented also in MPyC, so just in there. And what people normally do is Taylor series or other tricks. But this has some advantages. This can be done in pre-computation and it's not too expensive overall. And it's, yeah, random self.
Double bracket is the thing is encrypted or.
Yeah, secret shared. Yeah.
Oh, right.
Yeah, secret shared. But you may also think of it as encryption sometimes, if you like. But depending on the details. But yes.
In the science thing, that's the accuracy of your computation is suddenly play a role.
It does, yeah. So I wanted to skip over that here. We get back to it to that in a moment. But so these values, they are fixed point. We do it with fixed point values rather than floating point because floating point is very expensive. So yeah. So that concludes part 2, and now in part 3 I want to highlight some things about this MPyC library package. We've put a lot of things in there, so many of our research papers went in there as part of the library in a way. And for this occasion, I'm going to highlight a couple of things. So it was launched in 2018, but development was already started earlier in a way. And the development is still continuing, still adding things. But one main goal is usability of the library, meaning that the code should be simple and yeah, not involving lots of things. So this here is running code. So this is a Jupyter notebook. It runs as a single party because, well, there's no other parties here, but to run it with multiple parties is not much extra effort. What's the word again? The things that you have to do to get the system started, the blah blah blah, the word, the board, the board, the
overhead.
The overhead, yeah, but that's typical word. But I mean, to get running, to get started, if this package is on your system, it's just this single line, and there you have your multi-party framework available. And this is running code. This will run by creating a type, secure integers default 32 bits, generating a random value of that type in this range, uniformly, perfect uniformity. And now in this simple case, we open that, and then you have a lottery, but the actual use is by running it with maybe 10 parties, if you like. And then nobody should be able to influence the outcome of the lottery unless there's a big collusion. But that's the idea, this usability. And yeah, by also providing lots of built-in primitives. And here you see the main types that are built in. And these are these fixed point values. And that's what we do in not only in MPC, but also in FHE and similar things. we use fixed point rather than floating point, because floating point, when you do that securely, is out of the question. Well, we do it, but it's going to cost you. This is relatively slow. And it's not so much floating point multiplication that is slow, but rather addition. I have a slide on that. And then here, this is also a very powerful thing, secure groups. There's a lot behind this, even up to class groups. You heard of class groups, class group cryptography, and elliptic and hyperelliptic curves are behind this with a very simple interface. So I just learned today that Robert Record had the equal sign for this. So I'm using this here for the group operation for good reason. So if you know Python, this sign is used for matrix multiplication. That's the default notation. And it's nice because it's asymmetric. It's asymmetric and matrix multiplication is not commutative. And this denotes the group operation. And if you think about representation theory in mathematics, that all revolves around matrices and matrix multiplication to represent arbitrary groups. So it makes a lot of sense to use this as the abstract group operation. This is for the inverse, and this is for taking powers. But you can just use that interface to, for instance, to do an election like this. So this is the homomorphic election scheme with algorithm encryptions. We do a key generation. We just saw how to generate a random integer in the range 1 to 10 million or something. This is similar to generate a secret key uniformly at random along with the public key. So this is the secret key X and H. In the program, the X just shows there, but this is maybe misleading. That X is secret shared, so nobody is going to see it. The H is a public key, so that's actually opened, everybody can see it, but the X is never existing anywhere in one place, only in secret shares. Then in this little mock-up, we let each party encrypt a random vote, and for the demo, I just do generate this at random. It's an algorithm encryption, but this is the notation. So this is the vote, and inside the randomness is used. But this is the notation for taking the exponent, e to the power of v, in the abstract group notation. They exchange this. Transfer is just exchanging things in the clear, but these are encryptions. Now everybody has an encryption of everybody else, and we take the product. We're going to homomorphically multiply these algorithm encryptions that contain two components, and this is the group operation. So this is all that it does. But in this case, this is done in the clear, so that's very quick. But it could also be done that these group elements are secret shared and nobody sees the group elements. And then we decrypt using the private key and compute the result. But it's relatively simple.
So this is a situation where each voter is participating entirely.
Yeah.
This example.
Yeah, it's like a boardroom election.
Okay.
We could run it between all of us, and then secure fixed point arithmetic as an alternative to floating points. So the problem with floating points, if they are secret, is that they have a different exponent. So you have number A, number B. This has exponent 10 to the power 5. This has exponent 10 to the power -7. When we have to add them, we have to align the radix point. But that has to be done securely, privately. And aligning means that we have to look at the bits and see where, and that's very expensive. That kills the performance. It is available, but it's not so fast. So what we normally do is we fix the radix point by keeping the fractional bits the same number and there's no exponent. And then we do things like I just showed to compute all these things in a relatively efficient way, but you have to design your algorithms, your protocols to work with this precision, and you have to make sure that the precision is sufficient and that it's not overkill, because if it's too much, it will slow down the thing. Another direction is to use vectorized processing all the way through. That will reduce the overhead considerably. And it's available for these three basic types. So much of it is also vectorized. And then here we go again in this direction that I already mentioned, is threshold crypto. It works in terms of these groups, and these are available. But it means that an element of the group is also not available in any place. It's only there in secret shared form. And when we do a group operation, the secret shares are combined by the software, and there's communication taking place. So one such application, by means of Python operator overloading, will have a routine, coroutines invoked between all the parties, and lots of things will happen. But yeah, it just works. Yeah, and here, that's a direction that I want to talk about more than this here, but sometimes we also want to make the results verifiable. Like a zero knowledge proof is verifiable by just checking it without interaction. Sometimes we want to extend the PC with this here. And in a way, generating a zero knowledge proof by a single prover is a special case of MPC where you only have one party. So then everything falls into place. Almost there. Just to show you another aspect, is what the student of mine is to make sure. So for instance, we want to do a multi-party computation on our smartphones. But that would be rather complicated because we have to connect to each other by peer-to-peer. And then I have to write down your internet address, but you probably don't know it, and you're on your telecom network, and maybe you are on the Wi-Fi here, and that's terrible. So with peer.js, peer JavaScript, you're able to connect via some server, and you talk to begin with the central server, but via hole punching and stuff, you will get really peer-to-peer connections with the other ones. Then the server is not in there anymore. So then you can establish that kind of connections, and then you run the MPyC, and in this case, the whole of the MPyC is running inside the browser. So it has to be compiled to WebAssembly. The CPython has to be compiled, and then MPyC without modifications is run inside the browser and doing these things. So yeah, I had where are we? Oh no, maybe now it's time to stop. I will not try to demo that one, but this you can find the link on the internet. You can run it for yourself, and it sometimes runs with the smartphones. There's lots of technical details, but it runs. We have been running it with several smartphones. This kind of things, and even these demos, neural networks, the MNIST thing, all that kind of stuff is in there. And with that, I want to close and have any questions. I guess.
So at one slide you wrote that this every function can be represented as a circuit of plus, and
Yeah.
additional, and from there you can take it to polynomials. So does polynomials also often appear in MPC?
Yeah, so what do you mean from there you can take it
So you
polynomials?
can any time like compile any circuit into polynomials, right?
Yeah, if you like, yeah, that's something that's depending on the frameworks, sometimes CK snarks or so,
Yeah,
that kind of things, they work in some model that involves polynomials. Yeah, that could be the case. But those generic pathways,
yeah,
they will be totally unsatisfactory performance-wise, because if you do an MNIST computation and you translate it to a binary circuit, the circuit will be huge. And so maybe you can still claim polynomial running time in theory, but it has no practical significance. So that is only to show that it's basically powerful enough, but it's not the practical route that we can follow.
right.
Yes?
So thank you, very nice talk. My question is, of these algorithms, are these formally verified?
Yeah, good question. Not yet.
Not yet?
No. So now, from, I mean, maybe some of the published algorithms. I don't know. There's not much going on in that direction, but all this code is there's no direct verification of these as a whole or so, maybe pieces or so, but that's not done yet. But this company I mentioned, Roseman Labs, they are also looking into maybe formal verification, or at least they will have audits at all kinds of levels, and they also want to go for the next level. And so there are some serious looks at the code, but that's still far from formal verification.
That would be my next question. Is the algorithm verified, or is the implementation of it verified?
Yeah.
That would be my next question.
Yeah, so there are security proofs of the higher level approach. So within cryptography, sometimes we do security proofs in the ideal real model with an ideal functionality, and then it's proven that certain protocols implement that functionality in a strict way. And small pieces or the basic protocols for secure multiplication have been verified like this, but doing the larger compositions hasn't been done that way. Although many of the protocols, they use the primitives in a black box fashion, and then there's not much to prove, because the things compose already without problems. So there's lots of easy parts in a way, and it gets tricky when you do a protocol that opens up special values. Then you have to do more work.
It's very interesting. I taught cryptography 15 years ago in this department, and then I stopped to follow it. I stopped teaching it, and I also stopped following what's going on.
Yeah.
So, and it's impressive to see what's happened.
Yeah, the last 50 years were enormous, but it's partly because of blockchain, but also people. So in the old days, when you had a crypto paper, it sufficed to sketch the idea, maybe say something about why it would be secure, have a partial proof or so, etc. Now, often papers are very extensive in a elaborate security proof, which you might rightfully not trust always, because those manual proofs, they are very error prone, and nobody is really able to verify, and there are mistakes sometimes. And also what people do is implement things more. So they will. So it's often a paper is done by a team, and then they actually implemented it, and they run check for the performance and stuff. And that also made everything bigger. Or I mean the whole crypto topic, the number of crypto papers. If you check the ePrint ISCR ePrint server, maybe not, we should check it now, but it's maybe already over 2,000 papers this year. probably close to that, so 2,000 crypto papers every year. And those papers, they got longer also on average, so it's quite huge. Yeah?
Oh, no, go ahead. Can you go back to the slide with the three-party bit intersection? So Alice, Bob,
Yeah.
and Chuck, I have a question about the attacker model base. So what we assume that, so if say Chuck is dishonest here,
Yeah.
can Chuck eavesdrop on the communication between Alice and Bob? Because if he can
Yeah.
do that,
Oh, so
he
yeah.
I think he can compute X and Y, right?
Yeah,
So we assume that
there
he
should be
cannot-
private. There should be private communication,
Okay.
which Chuck cannot see,
Okay.
and also this cannot be seen by Bob.
So then the attacker model here is that each one can see their own local
Yeah.
things, and then only what they're explicitly sent by someone else.
Yeah. So what they are meant to receive, that's what they see.
Okay.
And also, so for Alice, this is the view,
Right.
and they should not here. This only tolerates one corruption. So if two parties collude, then they see everything because alpha and
And anything else can.
Yeah, if
Of-
the
of-
Chuck and Alice,
Chuck and Alice, yeah, then
then you get. you can easily
because
get white.
Chuck has beta, then
Yeah.
you have Y as well. Yeah.
You assume secure communication.
Sorry?
You assume secure communication.
Yeah. So no eavesdropping basically, and then they can all see the intersection, I imagine. So okay, so that's
Yeah. But so secure communication is assumed throughout. So in practice, the parties are peer-to-peer connected via SSL connections. That's the thing. Yeah.
So I just wanted to maybe ask a slightly different question that, how could you integrate MPC with something like federated learning? Because in federated learning, when you're building an independent model,
Yeah.
and, because I see a lot of similarities in the way you would do independent model construction, assuming non-IID type environments where you could do model aggregation in some way using
Yeah.
MPC.
So often in federated learning, each of the parties, let's call them parties, they do the local processing, and then it's like divided into epochs. Then at the end of the epoch, they want to exchange some information so that they are all on the same level, so to speak. But in ordinary federated learning, these exchanges are done in the clear.
Yes.
And it's hoped or assumed or accepted that those are safe to exchange and don't leak too much information. But with multiparty, you can make that exchange secure, and that you only get the average. So you want to establish the average of what all the parties have, and all the parties will learn the average, but they won't see the individual inputs.
Yeah, I mean, federated averaging is just one approach.
Yeah.
There's a whole bunch of aggregation techniques.
Yeah, averaging is the simplest one, but you can do. Yeah.
But one thing was that how do you know the correctness of the aggregate model? So suppose, because when you do aggregation in this context, how would you verify correctness?
Well, you could run, so if you done 20 or 100 epochs or so, and then you want to see, is the model any good? Then you could take the model as it exists, and run it on secret shared data as a further MPC computation. And depending on the complexity of the model, if it's only to test the model, so to do classification, say, that might be quite simple, efficient. So you can run it on test cases and see if it.
Like a benchmark.
Benchmark it.
Okay.
And you do that all in MPC. But the bulk of the work, the local federated learning is still done locally and therefore quickly.
Okay, very interesting.
I have a student now, he's about to finish his thesis, master's thesis, for survival analysis in medical stuff and survival analysis. And he does everything in MPC, so generating the model, but also doing the model assessment by the concordance counting but everything in MPC and in MPyC actually.
Right, so following this question, let's say like, is it possible to achieve this MPC thing where you a priori force each party to commit to their data set
Yeah.
and then train them and then prove them later that they have run on the right data?
Yeah. So then you're getting into verifiable MPC.
Yeah, that's what.
And verifiable MPC has indeed two sides. On the input side, that the inputs are say certified, that you don't use other inputs. Like if you do the millionaire's problem with your salary, you can say anything you want. It's not very helpful, but we could have the tax authority, our tax returns, they could put them in encrypted or secret shared form with a signature on it, and your tax return, etc. And then we compare the salaries from the tax returns, and then it's more meaningful.
So that's like federated learning in reverse, right? Because you have the model, go to verify the correctness.
Yeah, I mean, you're forcing them to a priori to commit to whatever data they have, and then learning.
But commitment is the right word, So and the commitment could live on the blockchain or something in encrypted form, and from that you could decrypt it in a threshold fashion and turn it into secret shares. We've done also that kind of stuff, and then there's also the output. So the output that's produced by this long computation. It looks like a random value, the secret shares and stuff, and but we can make all this stuff verifiable by attaching certain zero knowledge proofs. But that's costing a bit. So to then
that definitely.
But there is, for instance, it has to do with like NP, the NP completeness, the class and non-detwist. So there's the big gap between verification and computation. So verifying the solution to an NP problem is polynomial time, is quick, but computing the solution is hard. But so if we first compute the solution in MPC, then the verification in verifiable MPC can still be fast. So for instance, we did linear programming with the simplex method. Then you have these certificates of duality, of the optimality, the certificate of optimality for the solution to the convex by the simplex. So you do maybe a million iterations to find the optimal solution, and then you do one further iteration to compute the dual part, and that's already enough to do the verification. So you only produce a zero knowledge proof about that final part. And that summarizes the million iterations. So often verifying is easier than finding. Yes.
So thank you for the next talk. Since the talk's title is MPC for person preserving computing, I'd like to ask some question on privacy. I'm also doing study about federated learning, so I've been always asked the same question. What is the difference between privacy and security? It's like so many secure today, but
that's a tricky question. So it's also just words. So I generally use secure if I don't want to make it more complicated or qualifications. I just talk about secure. So we generally talk about secure multi-party computation. We don't even mention privacy, but secure encompasses both integrity properties, but also privacy properties and other properties. So, but it also depends a bit, what the context is. What is a more fitting word? But I put the privacy preserving because the organizers had that title, and I wanted to stick to that title. But usually I even put nowadays I just put multi-party computation, MPC, because some people, if you put a secure, they're going to abbreviate it to SMPC, but that sounds horrible to me. I mean, it's you could say secure MPC. We also have to put the S there, but that doesn't make sense. MPC is what sounds good, and it already captures the whole thing. And it's not used in many other contexts. So there's distributed computing and all kinds of things, but they generally don't talk about multi-party. Then you're almost sure that you're in the cryptographic setting. But secure encompasses all the security properties, and one of them can be privacy. The other one in MPC is correctness. But depending on your situation or your context, you might actually explicitly talk about privacy and stuff. And ordinary crypto, secure communication, people use privacy also for that a lot. So yeah. Does it help you or?
It's fascinating. Thank you for that. Very good. Okay, interesting discussion.
Thank you very much.
Yeah, happy to talk. Yeah.
Is there anything known about limitations? Because somehow theoretical limitations of all these approaches. Because if you somehow do too many operations, then you can get all information out. So there must be a general limit of for how many operations you can use.
Yeah, so with this here, in a way, with MPC, there's no limit to the amount of operations that you do in a way. So if we view the computation as a circuit, then there's no bound on the circuit. But maybe you think of like if you run many of these computations and you publish the outputs, from those outputs that are exposed in the clear, and if you have a lot of them, that might be revealing things still. So if you do, that might be a concern, and then people talk about differential privacy to maybe to add some noise to those outputs, even though they are put in the clear. We make them a bit noisy to reduce the leakage or what you can gain from doing that. So it's also it has to do with this classical topic of Doherty-Denning, statistical disclosure of databases. It's anyone heard of Doherty-Denning? Old days, the databases that you have queries on a database, and for instance, if you can ask for the average income of all people in the room, you do that. But then if you can, the next query is the average income, but I leave you out from the group. And I also get that answer. Then I can find your salary from that. So that's that can be a concern, and then you might do something like differential privacy. And maybe another thing you're thinking of is with fully homomorphic encryption. There you have this limit on the depth of the circuit before you do bootstrapping, because of the noise accumulating in the encryption. But maybe that was not.
You limit the depth of your circuit of encryption. How to make sure that the depth is.
And there, well, they have a solution that was the breakthrough of Craig Gentry, that he was able to do circuits of any depth with fully homomorphic encryption because of the bootstrapping. So the infamous bootstrapping technique in those systems. That's a way to get rid of the noise that accumulates. So you start a circuit at the top, you go down there, the noise accumulates until a level that it's too much. Then you cannot decrypt anything meaningful. Then you have to get rid of the noise. That's called bootstrapping. And it's called bootstrapping because you're going to run a decryption of the stuff under the encryption and re-encrypt the result so that the result is without the noise and you continue. It's all fascinating.
So I have two silly questions. So the first one is all about applications. The first one is that because the MPyC is in Python, and if we implement an application, let's say in a different programming language, how easy to integrate with the libraries here?
Yeah, so that depends on the language. So there are all kinds of foreign function APIs between languages. So Python has a strong connection with C because it uses C itself, and that depends a bit. But yeah.
I think the second question is about the implementation. So you mentioned that there is a spin-out company that implement MPCs in C.
Yeah.
And in terms of comparing that to the implementation in Python, then
Yeah. So they can achieve higher performance because already because of using C++, but they they do compilation. Python is interpreted, so that has its pros and cons, and you can do the MPyC system. You can make one change. Also, if you want to find out something, you just add a print statement and you print and you say run, and also to run it in the browser, the interpreter is there, so nothing needs to happen. With other frameworks, you have to go through sometimes some complicated steps of compilation, and depends on the platforms, etc. So that's a difference. But also the company is focusing on three-party computation. So they optimized things for 3 parties, where the 3 parties reside in different clouds. So they picked European clouds for mostly 3 different European cloud providers to run 3 parties, and then they optimized for that, and then they can achieve higher performance.
Actually, can I just ask a quick question about that, if I may? So I was just wondering, the kind of computational overhead required to do MPC is often pretty high, as you just said. How would you do? Suppose I wanted to do it on edge devices or resource-constrained devices. Is there a variant to MPC where you can do it? Say, I want this level of computational power. What can I do within this domain?
Yeah.
Bound.
Yeah, so
to do that,
yeah, there's nothing automated in that regard. But actually this here, like if this is just bits, so this is almost no computation, and you can do this for a bunch of bits at the same time. And there was a student at ETH Zurich, and he used Raspberry Pis to also run with MPyC to do what is it? Airplane location. So multilateration. So there's a plane flying in the sky, and it has this what's it called responder? No, not a responder, but it's a beacon signal, or it sends. It flies there and it sends a signal, and then on the Earth's surface there are sensors who receive the signal, and they know their own location, and then they have this time. And several of those locations, they will combine it, and he ran that on Raspberry Pi. So, well, Raspberry Pis are not that much constrained, maybe, but depending on the whole calculation, it need not involve that much effort. So if lots of the things that you do are linear, so we do also linear systems, and those are relatively efficient. And if the linear system, in this multilateration case, if you have 5 or 10 sensors, it's a small linear system, that's still quick. And you have that.
Any other questions? Oh. Thank you, Barry, again.
Oh, that's.
So I plan to have a discussion panel, but I think actually we have a very long discussion after the presentation. So I say that we have that already. So I think we also need some time to so everyone want to talk closer to Barry as well before we end at 4 p.m. But also to spend some time with the tea, coffee, and the technical there as well. So please, thank you.
Yeah,
thank you. Yes, thank you, Roberto. I think I think that's for the online. I think we can finish here. You